Okay, hi everyone. I'm Scott from the Department of Linguistics. So one of the central questions in speech production research is how we go from mental abstract phonological representations into physical acoustic phonetic speech signals. These mental representations can't be observed directly, so there's lots of different proposals for them, usually evaluated based on elegance of analysis. Big picture is there's lots of types. The most simple one is something like what's usually called beads on a string, which is just a string, a linear relation of sound segments. These have been criticized because they really lead to maybe an incomplete picture of the acoustic signal. So some speech researchers have proposed other representations in order to better handle this. Especially without introducing another cognitive mechanism to get something more defined. So one of these are what are called articulatory coupling graphs, which are dynamical systems that each are representing articulatory goals and the phase relations between them. And so these automatically create what's called a gestural score, the music theme, that tells you activation periods for each articulatory goal, which then directly gets you sort of this full phonetic picture. So these are thought to be advantageous over the beads on a string because they give you both sort of that abstract phonological representation and the physical phonetic representation in one object. Now, recent work in computational linguistics has used model theory and logic to sort of compare different types of representations to see how relatable they are, or maybe how to translate from one into the other. So here I have a model of beads on a string, a model of the coupling graph that have sort of different labeling relations. Here everything is C or V for consonant and vowel, just to not worry about the articulations or the segments. And then what changes is the ordering relation. So here you just have regular successor. Here you have the different phase relations, so like 180, 180. This is in phase 30. And so what you can do is you can basically write these declarative programs using logic to translate from one to the other and see how much mutual information is shared between the two. If you can translate from one and then back to the other without losing information, we say that they're bi-interpretable. They basically share the same type of information. And so what's shown here is for all of these ordering relations, how you can translate from this beads on a string into the different phase relations required for the coupling graph. And here shows how you can translate from the coupling graph back into beads on a string, showing that these two representations are in fact bi-interpretable, and claims that they're qualitatively sort of different are ill-informed. And so this is part of larger work to compare representations in linguistics in hopes to also make a software involving these declarative programs as well.
I was going to say mathematical gobbledygook in there, but clearly it isn't. So can you give us a summary about what's being conveyed there?
Absolutely. So here, this is sort of the equations that get us from this type of structure to that type of structure. And they're defined, this output relation is defined in terms of input structure. So this says two elements are in this is a 30-degree phase relation. If they're both consonants, if X comes before Y, and there's not a Z that's a vowel before the X. So that would be 4 and 5 here, end up in that relation here.
So does that representation enable you to do some essentially algebraic manipulation?
Yes.
Automatically on it?
Yeah.